Hello, Finxters. Nice to see you. We're going to talk about iterators, iterables, and we'll talk a little bit about the Itertools module and some useful things there. Iterables and iterators are everywhere in Python. We usually aren't aware of them because syntax of Python hides them from us. Almost every time we manipulate a sequence type, strings and tuples are examples. We're using an iterator behind the scenes. An iterator represents a sequence of values, each of which is returned one at a time when the corresponding iterator is invoked. We'll just start by looking at Python version. Nothing particularly version specific here. We're going to talk about the iterator protocol, which is how iterables and iterators interact to deepen the understanding of the basics of Python and present some of the useful tools in the Itertools module, which can be super helpful. And we'll also look at why iterators can be much more efficient than standard containers. So what are iterators and iterables? A list is it's probably easiest to just show some examples. The list 1, 2, 3 is an iterable, and we can use the for loop construct to march through the elements and manipulate them. And everyone here already knows how to do this, but let's expose what's going on inside. So we've got a list L. If we look at what you can do with a list L, with this list, it has all these methods. And if we look here, we see there's a method under iter. That's an internal method, and that's what makes the list uniterable. We can call that method like so, and what we get back is an iterator. And if we look at its type, we can see that it's a list iterator. There's another way to get at this iterator. We can retrieve it with the iter function, which is a little easier to say and quite a bit easier to type. If we look carefully, we'll notice that these are not the same object. If we create a new cell and call it again, we get yet another iterator for this. The reason it works this way is that it might be necessary to have multiple iterators looking at the same object or their own copies of the same object, and not get so that they don't interfere with each other, because that would potentially cause errors. For our purposes, we don't really need this right now, but if you're using concurrency, you might have to be aware of this. So it's good to know that it's there. Okay, so having our hands on the iterator, let's look at what we can do with it. Here we have what makes the iterator an iterator. It's the next method. And calling the next method retrieves the next value from the iterable, the associated iterable. We can call this method on our iterator, and it does what we'd like it to do, which is to deliver the next piece of the iterable. Like iter and under iter, next does the same thing as calling the under next method, like so. Okay, so if you remember, we only had 3 items on our list. We've just grabbed the last one. If we call the iterator again, you'll see that Python raises an exception, the stop iteration exception, and this is the signal internally that lets Python know that there's no more elements to be retrieved from the iterable, and there are no more values left. So you can see what the for loop does behind the scenes. The actual code does something like this. It sets up a condition, retrieves an iterator from the object by using the iter or the associated method, and while the condition is not met, it grabs the next item by calling next on the iterator, and then it catches the stop iteration exception and satisfies the condition, and the loop is done. So that's how a for loop works internally. Okay, so let's build an iterator of our own that does something a little bit different to demonstrate how the pieces come together. This one takes an iterable, a step size, and an optional offset, and will return every nth element. We start by defining a class with its init method and its instance variables. Contents is just what we pass in, the iterable we pass in. Stride is the step width. Start is where we start iterating on the iterable, and we have a state variable that manages the stepping. We define its iter method just to return itself, and we define its next method. The next method grabs a piece of the iterable and advances the pointer, returns the value. And if there are no more values, it raises the stop iteration. So this works very much like a for loop, except that it delivers every nth item instead of every single item, depending on the stride and the start. So we can instantiate our object, take a look at it, check its type. We can look at its methods. We see that it has the iter method and the next method. And if we wrap a for loop around it and print it out, it works nicely. So what's going on here? We just take an iterable, and in this case, the range 10, in the iterator we've just built, and the for loop takes care of driving our iterator with next internally, and takes care of catching the stop iteration when we've reached the end. You could argue you could do the same thing with for loop and slices, and you'd be right, but this is really just for illustrative purposes, and if you need to build your own iterator, then you can do so, and you can define any behavior that you might need that isn't built into the standard for loop or other control structures. So why are iterators everywhere? Let's see. Iterators and lists and tuples, similar data structures, both represent collections of items that can be accessed one at a time. And they can be consumed or processed with for loops and similar constructs. Why use iterators at all? The reason is simple. Lists and similar structures consume memory for every item in the list, whereas an iterator can retrieve or construct each item as needed. And because of that, it only requires as much memory as it takes to store one item, and potentially a little bit of overhead. So let's look at an example of exactly what that can mean. If we build a list of 1,000,000 elements and get its size, we can see that a list of 1,000,000 elements takes 9 million bytes to store. So we've built this list out of a range, and that range is an iterator. And if we look directly at the iterator, we can see that its size in memory is only 48 bytes. So if, in fact, you were going to access this list one piece at a time, you wouldn't need to have used up those 9 million bytes. You could have just used these 48 bytes instead. So that's way more efficient. If that pattern is acceptable and usable for you, then it can pay huge dividends to implement an iterator for the object. And that's why iterators are everywhere in Python, and pretty much everything that can be an iterator is implemented that way. Okay, so now we're going to talk a little bit about the Itertools module, which is a collection of useful iteration patterns built out of the pieces, basically, that have been illustrated above. And the Itertools module contains 3 basic kinds of iterators: infinite iterators, finite iterators, and combinatoric iterators. And we're going to give examples of some useful ones. And you can take a look at the documentation, and it's whenever you have an iteration problem, it's a good idea to take a look at Itertools and see if what you need is already there. Okay, well, we'll start with the infinite iterators. And they keep yielding values until you stop calling for them. They're great for marking other iterables in some useful way. Excuse me. So let's have a look. If we zip a list, an iterable together with count, we get this essentially the same, very similar to enumerate. We can also use the cycle iterator to essentially, this is almost like enumerate, but with the modulus operator applied to the index. And if we need to attach an element, we can use the repeat iterator. As you can see, these things may come in handy in your day-to-day. Okay, finite iterators are exhausted when their inputs are used up. There are about a dozen of these, and they do a variety of things, but we'll give a couple of examples. Starmap is the one with the coolest name. Takes a function and an iterable and applies the function to the elements one by one. The iterable number of members of each element should correspond to the number of arguments in the function. And I've just built a function that takes 3 arguments. Here's in this lambda function, and applied it to this list of tuples of arguments. So if we execute that, we can see that the discriminants of these 2 sets of coefficients are 0. But in any case, it's just an example to show you that if you can apply a function of any number of arguments to a list of tuples, each of which has the correct number of arguments. Chain is very handy and it allows you to treat multiple iterators as a single sequence. So if we chain these 2 strings together and print them out, it's as if we had joined the strings or created a new string. Here you can see that we actually don't need to use up the memory to create a new string to add these together. These strings are already in memory. The chain pattern grabs the pieces separately, and no excess memory is used, as opposed to creating a separate piece of memory with the sum of these 2 strings. Okay. Moving on, accumulate captures all the intermediate results of applying a function of 2 arguments successively to each element of the input and the results thus far. So it allows you to capture running totals. You can use user-defined functions, lambda functions, or import from operators to use efficient implementations of Python's built-in operators with function syntax. So if you wanted to get the factorials from 1 to 10, this little formula will return that for you. If the default function for accumulate is add, so that allows you to accumulate running totals of a list or similar data structure. Next are the combinatorial iterators. They are extremely handy when you need to use a combination of items. So let's import all of these. Product does a very similar thing to a nested for loop. And it produces the Cartesian product of the of its two arguments. So we get the first element of the first list, and then every element, then the second and the third, just like a nested for loop would do. So if you're using a nested for loop to build this kind of structure, you can use product and do it more concisely. Permutations returns all possible unique selections of length n from the input iterable. So if you want to get all the combinations of two items from the list red, green, and blue, this is how to do it. And this can be very, very handy for certain kinds of problems. And combinations returns all possible unique selections of length n, ignoring order. So if there's no difference between green red and red green, then this is the method you want. So you can see that there are half as many items, since these are no longer distinct. And combinations with replacements allows you to do a similar kind of thing, but lets you take each item multiple times. So hopefully that'll get you a little bit interested in wandering over to the Itertools documentation and taking a look at the other things that are there, which may be very helpful to you. One thing that's very nice about that module is that in the documentation, at the end, there are a bunch of recipes for handy iteration patterns, and in the usual Python fashion, people have actually implemented those in another module called More Itertools that implements all the recipes in the documentation and many more useful patterns. And I'll just show you a couple of examples that might motivate you to explore that module. So from More Itertools, sometimes it's handy to be able to remove a level of nesting from list of lists, and the flatten function / iterator will do that for you. So this is a piece you don't have to write yourself. If you need to grab every pair of successive elements pairwise, we'll do that for you. So these things tend to be pretty useful if you need them, and they're there when you do need them. So I'll just show you one more. Grouper breaks the input into chunks of the size argument. So if you want to break a list into groups of n for processing, you can do it like this. We can't see what's going on over here, but we have a little bit longer list, and we're breaking up into groups of 3. So I hope that gets you a little bit interested in following up and taking a look, and I hope this introduction to iterators and iterables has been useful, and now you know a little bit more about what Python does under the hood, and it should deepen your awareness of iterators and iterables, since they're just about everywhere in Python, and may help you in your day-to-day coding. Thanks very much.